So this rational expression problem, it only has one really difficult spot, which is down here. The rest of it is pretty straightforward. It'll look like a lot of the problems we've done in the past. So one thing I really like to do is just unpack the difficult bits. So to unpack things in algebra, we could factor them. We could see this expression as a conglomerate of other expressions that are kind of multiplying in with each other. Kind of like how the number 6 is 2 times 3, or how x to the 5 we could view as, well, x to the 3 times x to the 2. These are all examples of unpacking things. Now, one great trick here is noticing that 2z to the 4 and negative 8z squared have a lot in common with each other. So they definitely have a 2. And they have a z squared in common. Now, if we were to factor those ideas out of this expression, we're essentially doing 2z to the power 4 divided by 2z squared, which is just z squared. And negative 8z squared divided by 2z squared, oh, that's really easy. That's actually just negative 4. Now, one tricky bit here is knowing this pattern you might not have seen for a while, which is a difference of squares. So we could rewrite z squared minus 4 as a, well, I'll keep this original term. We could rewrite it as z plus 2 and z minus 2. Now we have an unpacked expression. This is z minus 2, this is 3, this is 7. These are all very bare bones, simple terms. So coming back to this, let's rewrite this problem, but I'm going to give some space. And we have a new denominator for this second term. We've got this doozy. We've got this 2z squared, z plus 2. Cool. And when adding rational expressions together, we have to make sure they have the same denominator. And we're going to use the technique of multiplying by version of the number 1 so it suits our needs. So we have to think, and it might help to put brackets around this term. What's this left side? What's this denominator missing? Well, it's missing this 2z squared term, and it's missing this z plus 2 term. So we can multiply it by 2z squared over 2z squared. And we could also multiply it by z plus 2 and z plus 2. And yeah, you know what? I'll put brackets around here. It doesn't really matter, but it kind of looks like it's all in unison. And now look, they both share the same denominator, and I didn't break any rules. Now that they share the same denominator, we can add these two things together. So we can make like just a super denominator. So we get, oh man, I've written this denominator out so many times. I really don't like talking that much, but. And over here, we do have to expand the 3 in, and we will have to expand this 2z squared in. It's a little easier to kind of think of this as basically 6z squared times, actually, you know what? I'll do this in a different color. That did not make a different color. Hold it. Okay, 6z squared times z plus 2. And if we were to expand this, we get 12z squared. Oh, no, we don't get 12z squared. We get 6z cubed plus 12z squared. And my 2's look like z's. That is not making this very helpful. Okay. So on the top here, we get this expression that we just worked out. 6z cubed plus 12z squared plus 7. And this would be our final answer. There's not really much we can do. There's nothing I see that we can factor out on the top here. One thing to really note that's very, 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 very important are restrictions. So the restrictions here is z cannot be 0. It also cannot be -2. And it can't be +2. All right, let's look at the really hard one. This is a great one, actually. Okay, so for this problem, we are also going to break down and look at each one of these terms and kind of factor each one. See if there's anything that can be broken down into smaller pieces. So 5y plus 10 can definitely be broken down. We could factor it to 5. And we just get y plus 2. And now we've got this expression underneath. And notice there's a lot of y's hanging out here. And we could go up to y squared and factor that out. We could also factor out a 4. So whenever you find your factors, always write it down first. So we notice 4y squared is common within everything. And now let's go piece by piece and divide each object by 4y squared. So 8y to the power 4 divided by 4y squared just gives us 2y squared. Now we're on 20. So 20y cubed divided by 4y squared is 5y. And 8y squared divided by 4y squared, well, that's just +2. Easy peasy. And we're actually going to be factoring this even further later, but I like to show everything kind of all one layer by one layer. So let's look and continue this layer. Let's look at the top here. 2y squared plus 6y. What's in common with these two objects? Well, they have a 2 in common, and they also have a y in common. Now we think, okay, when we factor that out, what's left over? If we do 2y squared divided by 2y, that's just y. And then 6y divided by 2y, that's just +3, plus 3. Now let's look at the denominators. What do we have in common here? The largest factor I'm seeing in terms of numbers is the number 8. And for y, It's y to the 3. That's the largest y term that we have. So let's factor out 8y to the 3. And what are we left with? 2y squared. Because 16y5 divided by 8y to the power of 3 is 2y squared. And then 40 divided by 8 is 5. And that gives us y to the power of 1. And then negative 24 divided by 8, that's negative 3. And, well, y cubed, easy peasy. That cancels. Now we're going to have to recall on some old memories with, I think it's called complex trinomial factoring. Not too great with the terms for these things. But let's look at each one of these separately. Let's factor them. So 2y squared plus 5y plus 2. Remember, we have to multiply the first and last term to get our multiplier. So we're looking for two numbers that will multiply to 4, because 2 times 2 is 4. And they're going to have to add to the middle term. I always have to add to the middle term because we're essentially breaking down the middle term. We have to add to 5. So what two numbers could that be? Well, I'm seeing 4 and 1. So we're going to rewrite this expression and we're going to factor it. And we get 2y squared plus 4y plus 1y plus 2. Well, can anything be factored in terms of this first chunk, this first group here? Yeah, they have a 2y in common. And when we factor that out, we just get y plus 2. And in the second chunk, the only thing that can be factored out is really just the number 1. So we have one group of this y plus 2. So we have one group of y plus 2. And then notice we have y plus 2 in common between both of these groups. So we can factor that out. Y plus 2, bracket, and then 2y plus 1. Now over here, we're looking for the same type of pattern, looking for numbers that will multiply to negative 6, because 2 times negative 3 is negative 6. And I'll show the little multiplier sign. And they have to add to positive 5. They have to add to 5. So what two numbers are they? I'm seeing 6 and negative 1. So instead of writing 5y, we can write 6y minus 1y. It means the same thing, but it lets us play it out and get really great factors. So 2y squared plus 6y minus 1y minus 3. Looking at this first group, we could factor out a 2, and we could also factor y. So we could factor out 2y, and we're left with y plus 3. And the second group, well, we could factor out a negative 1. We factor out a negative 1, it's going to switch the signs of both of these, and we get y plus 3. Whew, amazing. We got the same thing. It's a good sign. Using the same pattern as before, we get 2y minus 1 and y plus 3. All of that just to unpack the denominators. But something interesting happens when we rewrite these terms in. So we're going to rewrite this expression up top. And I'm going to rewrite the top. We've got this 5. I'm going to switch it up. We'll use circular brackets. Y plus 2 plus 2y y plus 3. And now I'm going to use these two expressions that I factored out to show the denominators. So we get this y plus 2 term and 2y plus 1. And we have this 2y minus 1 term and y plus 3. Now notice anything kind of screams out to you in terms of cancellation. We have this y plus 2 that could cancel, and we have this y plus 3 that can also cancel. Now, one thing to make note, very, 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 very important to make note, are restrictions. So it does exist, there does exist a time where we cannot evaluate this expression at y equals -3 or y equals -2. So before canceling anything out, we have to put that restriction in. We have to make note that this did exist. And it's kind of spooky because it's going to disappear, but it really does exist. And man, math gets weird sometimes. So just a note, y cannot be -3, and it also cannot be -2. And now we can cancel things out. So that cancels, that cancels. And by cancel, really, it's just becoming the number 1. It doesn't really like go away. It's just, it exists as a version of the number 1. And when you multiply things by 1, it doesn't change how those things are. So what we really have here is a bit of an easier expression than before. I guess significantly easier. 5 over 2y plus 1 plus 2y over 2y minus 1. Actually, you know what? I'm going to give some space here just to make it a bit easier, just like before. And I'll put brackets around these so we can see. Now, just like before, we are going to have to multiply by versions of the number 1 so that this all works out nicely. The version of the number 1 that I'm seeing here for this group could be 2y minus 1 over 2y minus 1. It's because it's missing that 2y minus 1 group. And vice versa, on the other side, this is missing the 2y plus 1 group. So we'll multiply it by this version of the number 1. Beautiful thing happens. We get the exact same denominator. Let's see. So we end up getting 2y plus 1 2y minus 1. And then on top, well, we're going to have to do some expansion and some collecting. We get 10y minus 5, because 5 times 2y, 5 times -1, plus 4y squared plus 2y. And we're going to have to do some more collecting. We can collect these terms, rearrange them, and collect things up. We notice the 10y and the 2y, that makes 12. When it all comes together, we get 4y squared plus 12y minus 5 all over this expression. Oh my gosh, we're gonna have to factor again. Wow, what a problem. The hardest part is figuring out which color I'm gonna use. Okay, so let's look at two numbers that multiply. They have to multiply to make negative 20, because 4 times negative 5 is negative 20. And they have to add to make 12. So they have to add to 12. Ooh, and those two numbers. Okay, so I just did some checking, and it does not factor nicely. You would need quadratic equation. And well, because of that, we know it's these two things at the bottom are not going to cancel out either. But because of what we have at the bottom, we can add some new restrictions. We know for a fact that y also cannot equal negative 1/2, and y cannot equal positive 1/2. These are very important. Okay, and this is the simplest that we can kind of break down this equation. This would be a final answer.